Hi everyone! In this video, I'll introduce you to Continuum robots in under 3 minutes. I assume you already have some backgrounds in robotics, so you won't be explaining the technical term. If you're watching this, it means that you are looking to learn about Continuum robots for the first time. First of all, welcome to the world of Continuum robots. The simplest way I can define continuum robot is continuum robots are controllable continuous structures. What do we mean by continuous structures? Consider a rod. A rod has a rigid and inflexible structure with a fixed shape. In contrast, consider an elephant's trunk, fully flexible. The elephant's trunk can take on various shapes, and such a structure is called a continuous structure. Now let's talk about the modeling process. Modeling and control of Continuum robot is pretty challenging. I don't want to explain the modeling here, but just want to discuss why it is challenging. If you check the channel, you will find multiple videos discussing various modeling approaches for Continuum robots. In this image, you can see the KUKA robot as a very common example of rigid robots. Structurally, these robots are composed of a series of arms and joints where typically each arm is driven by a motor or actuator that ensures its movement. The robot's degree of freedom are determined based on the number of links, joints, and any motion constraints. Having distinct and clearly defined arms and joints in these robots make modeling much easier. We only need to assign a series of coordinate frames to the joints, and then following the de novo Chartenberg convention, we fill out the parameter tables, which allows us to derive the robot schematic. Using the methods like Lagrange, we can then extract the dynamic motion equations for the arms. Together, these equations provide the complete motion dynamics of the robot. On the other side, the challenge with continuum robots arises from the fact that they don't have the distinct links and joints. The robot's body is capable of covering a continuous range of shapes. Their degree of freedom are infinite, and along with this, they only have a very limited number of actuators. This places these type of robots under the category of underactuated robots. Now let's take a quick look at the internal structure of this type of robot. In a simple example, beneath the surface there is a backbone or central spine which serves as the support or backbone for a series of discs fixed at specific intervals along the backbone. These discs act as guide or support for a set of actuating cables, which serve as the robotic arm. The cables are attached at one end to the distal end of the robot and at the other end to a set of motors. When the motors move, the cables are tensioned, and to compensate for the elongation in the cables, the backbone bends. This process enables the robot to achieve various shapes. Now you know what is a continuum robot and why their modeling is challenging. If you're interested to know more about their modeling, don't miss my other videos discussing in detail different modeling approaches of continuum robots. Thank you for being with me today, and don't forget to like, follow, and subscribe for more